Hello, folks. Okay, well, this time, given the confusion that I created around our quad trees last time around, I just wanted to talk a little bit about how our addresses, items, and quad trees are organized and how things like the insert and search and print and whatnot work in our demo program. So, hopefully we can make this reasonably understandable. We'll see. So, the idea, again, is that we've got some two-dimensional space and we want to describe things within that space. So what I'm going to do is have an address string that tells me what part of the space something occupies. So we'll have just the empty string is going to represent the entire two-dimensional space, the whole global space that we're looking at. And as our addresses get longer and more precise, they're going to be talking about smaller and smaller pieces of that total space. So the way we're going to do it is to just keep breaking things up into smaller and smaller quadrants. And for each of them, for each quadrant, the digit 0 is going to represent the lower left corner, a 1 for the upper left, a 2 for the lower right, and a 3 for the upper right. So if I use just the string 0, then I'm talking about a quarter of the global space. So essentially just one corner of that space. Or again, if I talk about just the string 1, I'm talking about 1/4 of that space. If I use strings like 00 or 01 or 02, then I'm talking about a quarter of a quarter, right? We look at the first digit to find out which quarter of the overall space we're interested in, and then we look at the second digit to find which quarter of that. So 00 means, okay, go into the 0 quadrant, if you like, and within that, go into the 0 quadrant in that. So it's breaking it up into 16 pieces instead of 4. And again, if we went to a 3-digit address, that would be breaking each of these 16 up into 4 even tinier ones, right? So 000 would be the bottom 16th of this overall space. So we've got this notion of we can break our total two-dimensional space up into smaller and smaller, more precise units. And we can talk about any one of them just by using an address string. So that's all well and good for describing things that just exactly fit one of these squares. But what if I want to talk about a region that kind of crosses some of these boundaries? Suppose, let's say we wanted, the two-dimensional space we wanted to represent was a map of our campus. So here we've got a map of the VIU campus in Nanaimo, and I want to represent some square where the math physics building lives. So I decide, okay, well, of my overall map, where does the math physics building sit? Maybe I decide that it sits right about here, right about where this 10 and 12 are. So just kind of up in here in my overall space. Well, that doesn't fit, it's not exactly the same as 1. It's not exactly the same as 10 or 12, right? It's some combination of the two. So for regions that I want to describe, I'm going to be kind of lazy here and just describe them as a rectangle. And so what I'm going to do is specify the lower left corner of the right rectangle and the upper right corner of the rectangle. And so for the our math physics example here, our rectangle might just consist of these two squares, 10 and 12. Or maybe I decide that, let's represent the library, and maybe the library covers these 4 squares, 21, 23, 20, and 22. So to describe where the library lives, I'd say, okay, well, the lower left corner is 20, the upper right corner is 23. Or again, in any combination you like, right? Where you want to describe a region, you just say, okay, well, it covers from here to here, or from here to here, whatever the lower left and upper right corners happen to be. So now we've got our division of space into our sort of quadrants, smaller and smaller quadrants. And what we're going to do is use our quad tree to break up our space this way. So the top level of the tree, the root node of the tree, is going to represent the entire global space. Its 4 children will represent those 4 quadrants. Their 16 children in all will represent, those 16 quadrants, right? The 4 children of each of these things. And when I want to describe an item in my space, what I'll do is come up with a name for the item, math, physics, building, a description of it, whatever, and blah, blah, blah. And then the addresses of the 2 corners. So I create this item to describe my building, and I want to insert it into this tree so that my quad tree is going to have a list of, all the buildings on campus, for instance. Well, which node do I insert it in? I could put everything in the global space, but that doesn't help me much, right? I don't really need a quad tree if I'm just putting everything in the root. So what we'll do is we'll just take the item that we're inserting and push it as far down the tree as we can go and still have it fit entirely in the current node. So, for instance, if our math physics building covered the 2 nodes 1, 0 and 1, 2, it can't go down to that bottom layer because it doesn't fit entirely in either one of those. But we can put it in our middle layer here. It does fit entirely in quadrant 1. So anytime somebody comes up with a new item and they've described which regions it covers, we just say, okay, let's insert it in the tree and we'll push it as far down whichever path it goes to the smallest node that can completely contain it. And that's going to be the notion of the quad trees that we're using in the demo program. We'll have the address strings represented using one class. We'll have the items that we're describing represented as a class of their own with the name and description and the addresses of the lower left and upper right corners. And then we'll have the quad tree as a whole as the storage unit for these things represented as one more class. So, just in terms of a couple of the details, again, I think most of this I've just gone through and described, but we're talking about an item covering a rectangular area specified by the addresses of the corners. And as we looked at there, when we're looking at these things, 0 and 1 are to the left of 2 and 3, and 0 and 2 are below 1 and 3. So when you're looking at which of the 4 corners things are, and when you're trying to figure out lower left or upper right. We'll let the user go through, and when they're describing the address of one of the corners, we'll let them enter just the first part of the address. So if they enter, let's say we've got 10-digit addresses, and they just type in 1, 3 for the lower left, then we'll assume that they mean the very lower left corner of 1, 3. So we'll just pad it with zeros. And the same if they enter a partial address for the upper right, then we'll assume that they mean the extreme upper right corner of the region they specified. So we'll just pad the address that they gave us with 3s. So I think in the demo program we use a maximum address length of 10. So it'll just always pad addresses out to the full length, either with zeros for lower lefts or with 3s for upper rights. Again, if we're thinking about how big the area covered by any node is, by any region, if we look at the longer addresses, every time you add one more digit, you're cutting the size of the space represented by a quarter. So I think that should hopefully be pretty intuitive. Again, if we're looking at where things are located, we're just pushing as far down the tree as we can go and still have the item fit entirely in that node's region. Again, this is just exactly what we were looking at in the previous example. If we've got an item we want to insert, we look at where it fits. You start at the root. It's obviously going to fit in the root. If you can, you push it down one more layer and see if it fits entirely in the address space for one of those. If it does, then you see if you can go one more layer, and you can just keep going down like this. Now, what's nice is that we can look at the lower left and upper right addresses, and right away we can tell which node they're going to belong in. So if somebody gives you the 2 addresses, so they give you an address for the lower left and they give you an address for the upper right, if we look at those 2, they both start off in quadrant 0. So we know this is going to fit in quadrant 0 because the lower left corner is in it and the upper right corner is in it. And then we keep going. They're both in kind of the one subquadrant of that. So again, they can both fit in the 0, 1 node, right? Both the upper right and the lower left are inside that. So we know we can go down to the 0, 1 node and it'll work in there. But once we get past that, they start to differ, right? They're in different subnodes, right? We go to node 0, 1, 1 for the lower left and node 0, 1, 3 for the upper right. So we can actually look at these two strings and say, okay, well, look at the common part, look at the part that's the same in both of them, and that identifies exactly which node our item should be inserted in. And so that's essentially what's going to go on. When a user enters an item, they're going to give the lower left address. It's going to get padded with zeros if necessary. They're going to give the upper right address. It's going to get padded with threes if necessary. And then we'll look at those two addresses, take the common prefix at the front, and say, ah, there's the node this is going to go in. Now, you can have lots of different items stored in each node, right? If you go back and let's pop our way back to the beginning there and think about our map example, maybe we've got one building that goes from 2.3 to 3.2. So that's going to have to go into the global space, right? It can't fit in 2, it can't fit in 3, it's got to go in the global node. Maybe we've got another one that goes from 0.2 to 2.0. Again, that spans 0 and 2, it can't go in either of them, it's going to have to go in the global node. Maybe we've got another one that's, going from 0.1 to 1.2. Again, so it's spanning multiple of the second layer nodes, it's going to have to go in the root node. So there are going to be lots of cases where we've got a bunch of different items stored in any one particular node. So each node will maintain a list of all the items it's keeping track of. Right here. So we take a look at where an item goes, jump our way down to that particular node in the tree, add that item to the list for that node. So again, if we look at back to our original tree there, if somebody decides that they create an item where the lower left is 0.3 and the upper right is 3.0, so it's going, the lower left is down here, the upper right is up here, then we're talking about covering those 4 squares. It can't go in any one of 0, 1, 2, or 3 because it's kind of overlapping all of them. So it gets inserted in the global space, the global node, the root node. If they then go through and create an item that's going from 1.2 to 1.3, so it's these two nodes here, or these two rectangles here, that'll fit entirely in 1. So when we go to insert that, and again, you can see looking at the prefix strings, right? They've got the one common prefix string, so they go in the node 1. If we look back at the previous one, they had nothing in common at the start of their string, right? So the prefix string is essentially the empty one, so they go in the global space. So we can go through and just keep creating and inserting items into our quad tree, and it's keeping track of where everything is. All right, just a couple of observations on the demo program before we play with it for just a second here. It does require you to create your original quad tree before you start inserting into it. When you go through and create items to insert, it asks you to come up with a name, so basically just a few words on what you want to call it, a description of it, and then again it asks you to provide the lower left and upper right addresses for the region that item covers. And again, it pads the lower left with zeros, pads the upper right with threes, and the maximum length that it's using right now is 10. It follows the rules that we just described on where the item gets inserted in the tree. And then later on, when you decide that I want to search the tree and try and find an item that's in it, or when you try and do something like print the tree, it'll give you the option, do you want to print just the stuff that's in one specific node, of the tree? Or do you want to search just the stuff that's in one specific node, that one node's list? Or do you want to search that node and its entire subtree, all of its children as well? So for each of those cases, it'll ask you, do you want to do just the one node, just the one node, or the entire subtree? And then it'll ask you, well, okay, so which subtree or which node is it that you want to search or do you want to print? So you're going to have to first make the decision, node or tree, and then specify the address of the node or the top level of the subtree that you want to print out. So with that in mind, let's just do a quick play with our demo and see how badly we can break things. So if we're in our project repository and we've done a make, I've already compiled this before, so it's currently up to date. We run our demo program. And again, it goes through this process, prints out the menu. If you hit the V, it'll just turn the verbose mode on or off, so it'll give you more or less information as it's running through. Just H to display the menu, etc., etc. So we need to create a new tree. It'll complain if we try and insert before we try and create a tree. So create a tree and then start inserting items. And again, you go through and specify, okay, I want to insert an item. It's, I don't know, my building A. This doesn't have to be representing a map. It can be representing any kind of two-dimensional information that you're interested in. But let's say I want to create a building A. That's my fancy new building. And we want to specify the two addresses for the lower left corner and the upper right corner. So for my lower left corner, I say it's going to be in position 1, 2, 3. And for the upper right corner, it's going to be in, I don't know, position 3, 3. And again, it's padding that first one with zeros and the second one with threes. So let's just try printing to see what it inserted there. So I do a print. And it's going to ask me, do I want to do a quadrant or the tree? Let's print the whole tree. It asks, which node of the tree do I want to print? Or just an asterisk if I want to print the whole tree. So I'm just going to print the whole tree for a moment. And we'll go off and we can see that it actually did go through and insert this in the tree, building A, my fancy new building, and it gives the lower left and upper right addresses for it. And you can see that it's padded them out with zeros and threes. So we go through and we decide, let's insert another one. So let's insert something that fits entirely in, if you take a look at this one, there's no common prefix string in these. So this is actually going to be in the global, the root node. Well, actually, let's show that. Let's do a print. And this time we'll just do the one node, right, that one quadrant, and we'll just use the global one. So just the stuff that's in the root node. And sure enough, our that one item that we inserted wound up inserted in that root node. So yeah, you go through, you can keep doing this sort of thing. Let's insert one that's, I don't know, some other building, someplace else. And we'll try and create one that fits entirely in node 1. So I don't know, give it address, start off at 101, and its upper right will be in address 13, or let's say 1301 or some such thing. And again, this should have inserted in node 1 because we've got 1 as the common prefix string there. So if we go off and again, let's just print the entire tree and hopefully it finds both of them. Yeah, it goes off and finds both. If we want to print just a single node, so if we try and print that one node, yeah, sure enough, it did wind up in the node that we were interested in. And so you can see the format that it's using here for the addresses is it's telling you what node it's in, it's telling you the left address or lower left address, and it's telling you the upper right address, and of course the name and the description. So that's the output format that you're getting. All right, you can delete the tree, you can quit, you can try and do searches and removes. I'll let you experiment with those, but again, they're basically working off the same basic ideas. When it gives you the prompts for quadrant or tree, you can follow the same sort of idea. And when it gives you prompts for addresses, again, you've got the same basic idea. So hopefully that's a little clearer than the original description was. We'll leave it there for now. And we'll see if we can actually quit and leave it there for now. Yay, so it deallocated and shut down. Okay, folks, we'll leave it there.